So, sir, you can start after 5 seconds.
Okay. Good afternoon to all of you and welcome back to the 20th lecture of STAR 2026. Today's first lecture is on photometry and astrometry by Dr. Priyanka Chaturvedi from TIFR, Mumbai. We welcome Dr. Priyanka to STAR 2026 session. Moderator of this session is Mr. Rishikesh Sharma from Physical Research Laboratory, Ahmedabad. I will briefly introduce the moderator. Mr. Rishikesh Sharma is a scientist at Physical Research Laboratory, Ahmedabad. He has developed the data analysis pipeline for the Parallax 2 spectrograph for high precision radial velocity measurements. His work also includes improving the precision of wavelength calibration for high resolution spectrographs. He has been involved in multiple exoplanet discoveries from the Parallax Exoplanet group at PRL and is currently pursuing his PhD in understanding stellar activity. Over to Mr. Rishikesh.
Thank you, sir. Good afternoon, everyone, and a warm welcome to this lecture session. It is my immense pleasure to introduce our today's speaker, Dr. Priyanka Chaturvedi. She is a faculty member at Tata Institute of Fundamental Research, Mumbai, since June 2024. Her research work focuses on the radial velocity techniques and stellar spectroscopy for exoplanet detection. She completed her PhD at PRL Ahmedabad in 2016, where she worked upon eclipsing binaries and radial velocity studies. After that, she held a short postdoctoral position at TIFR from 2017 to 18, and then extended tenure at the Thuringian State Observatory, Tottenberg, Germany, from 2018 to 24, where she was awarded a DFG grant as a principal investigator. Dr. Chaturvedi leads the Planet Working Group of International Calmness Consortium, which is dedicated to the search for habitable planets around nearby end-of stars. She is also actively involved in several international collaborations focused on exoplanet detection and characterization. In addition to her research, she is also an active mentor and science communicator, and also a member of Astronomical Society of India and the International Astronomical Union. Without taking more time, I would like to welcome Dr. Priyanka Chaturvedi, and over to you, Priyanka.
Thank you, Rishikesh, for the very nice introduction. And also thank you for ISRO START program for giving me this opportunity to speak with a wide audience. So I will be talking today about photometry transit as one of the exoplanet detection techniques, and in general talk about astrometry, and also briefly mention how it is being used or how it will be in future being used to detect planets. Okay, so we are aware that there are several stars which are around Sun, and as you can see in this nice picture, this is the constellation Orion. You see a star Betelgeuse, which is probably identifiable by many of you, and you also see that it has a hue, a color there, which is red in color. Then you see another one, which is the star Rigel, which has a color which is bluish. So what I mean to say that there are many stars in the night sky that we do associate colors with. And probably in the last few lectures, you would have been made aware that stars have a variety of temperatures and masses. So the luminosity is the total amount of energy in a way which is coming out of the stars. And this is the temperature of the star. So if you happen to draw a diagram which plots this luminosity and temperature, it's called the Hertzsprung-Russell diagram. Most of these stars lie on this diagonal, and the sun sits right in the middle. That's why you might have heard the term that sun is a yellow star, and it is also a main sequence star. So main sequence means that you are burning hydrogen and helium inside the sun to produce energy. There are many interesting stars, some of these which are fairly cooler than sun, which lie on this bottom right part of the diagram, and much hotter than sun, which lie on the top part of the diagram. So what I would like to emphasize here. Okay, so now this is the question which persistently all of us at some point in our life would have asked: are we alone in the universe? Well, there are so many billion galaxies in the universe, and every galaxy hosts thousands of millions of stars. So each of these stars could potentially hold a planet. So definitely, we believe that we are not alone. There are many such systems like us, and we would like to detect these. So the first one across a sun-like star was detected in the year 1995 by these two gentlemen, Michel Mayor. He was the supervisor of Didier Queloz, and they detected the first planet around a solar-like star, which had an orbital period of 4.2 days and a planet mass of roughly half of that of Jupiter. So today there have been close to 6,100 planets that have been discovered, and they're very different from what we know in our solar system. So for example, let me just bring this to reality. I would like to emphasize a little bit. So the period of 4.2 days is so small. Mercury orbits our sun at 88 days. So it's much further out than what we see. But here there is a planet which is so massive and so close to its host star. There are several methods by which these planets are detected, and this is shown in the graph here. So what you see here are the different detection methods, which are colored in all different colors. And these are the total number of exoplanets which are discovered across the year. So starting from 1995, when the first planet was discovered, till the year 2025. Majority of the planets are colored in purple, which are the ones which are discovered by the transit method, and the other ones in green, which are the radial velocity method. So radial velocity was the method used to detect this first extrasolar planet. But transit, as you can see, is the most successful method to detect planets. So in this talk, we will focus on the transit method and also touch a little bit about astrometry. Astrometry are the pink ones, but you can see that there is probably nothing here. But this is going to change very soon. So we will talk about this in the second half of the talk. So let us begin by what is the transit or the ecliptic method. It's very straightforward to understand. So this is a picture of the sun with some things shown up on the disk of the sun. What are these things? So these are actually spots on the surface of the sun. But you also see something very round and beautiful. This is our planet. This is like a planet in our, not our planet, but a planet in our solar system, Venus, which is transiting the sun. Okay, but it looks very similar to these spots, right? You could see that, but these spots would roughly remain static on the surface of the sun. It will move as the sun rotates, but the Venus will have its own orbital velocity. So as you see, the Venus is transiting sun. There are other planets which also transit different kinds of sun, right? So this is what is a cartoon to depict how the brightness changes across time. So when you see this cartoon, you immediately notice when the planet passes in front of the star, there is a decrease in brightness. So the same thing can be understood with this very nice NASA video that has been created. So you see that this is a planet which is transiting the star. And if you happen to look at the light curve, so this is called the light curve, the dip in the the dip in the light curve that you see is called the transit signature of the planet. So if one wants to look at if what is the period of such a planet, you would wait for it to come again the second time and do another dip, by which you will be able to find out what's the period of the planet. But one thing to understand is that a very special geometry is needed for such a transit. So if you have a planet which crosses from the center of the star, then the transit is very much visible. But it can also be detected when it passes through the edge of the star. Still, the transit will be able to be visible. But suppose if the orbit is face on, so we call such orbits face on. So these are edge on orbits where the plane of the orbit of the planet is perpendicular to the plane of the star. But here it is in the same plane. So you are observing it face on. So you cannot see the transit which is happening. In this way, and also in the fourth part of the cartoon, you see that the transit is just missed. So definitely you can comment that the special geometry is needed for a transit. So there are many systems which possibly would have a transit possibility, but we are not in a right geometry to view that transit. So somewhere from the universe, the planet will always transit the star, but we are not favorably located to look at those transits. So such planets, even if they exist, we will not be able to find out. That's the point I'm trying to make. Okay, so now given this, we understand how this is. I would like to pose a very simple question. You could think about it. Suppose what is easier to do? Is it easier to detect larger planets or is it easier to detect smaller planets? Because you would have a larger planet creating a sufficient transit depth, but a smaller planet will create a smaller one. Again, you would want to think about if the transit would be easier to detect when the planet is further out versus it is closer or situated closer to the host star. Now, how do we actually perform photometry? There is a whole process how to do it. It is relatively simple compared to other techniques in astronomy where we do spectroscopy or so. Maybe you have certain idea of what that is through previous lectures. In photometry, what we do is we have a target star and then we observe it along with several comparison stars, possibly of similar spectral type. So we spoke about the spectral type, like different temperatures correspond to different spectral types in the HR diagram, the Hertzsprung-Russell diagram. So we try to choose the comparison stars very similar to the target star, and possibly the stars are not intrinsically variable. Then, in order to correct for any atmosphere effects, because we know that light travels through atmosphere. So based on where the star is located, whether it is right on top of us, like crossing the meridian, or it is situated at a low elevation angle, then it passes through a lot of air mass, a lot of matter of air, which makes the stars light dim, which this effect is called as atmospheric extinction. So this reduces the total flux of the star that we receive at the instrument end. So this is only an effect because we are observing the star from the ground. That's why we need to make correction. A simple thing is to do is by doing differential photometry. So if you have the original star, target star, and the comparison star, you just take the difference between the two. The atmospheric effects will just be subtracted out. Now you do this study try to do it on similar spectral type stars with a good signal to noise ratio, then you should be able to find out or do photometry on it. So this is a typical image that you get, and then you draw apertures around it. Means you try to calculate in this red circle what is the total flux of the star, and you also calculate the background flux in this annulus region in the yellow portion of the annular rings, and then you subtract the flux in the red circle minus the flux that you get in this annular ring to find out what's the total flux from the star. This can be converted into magnitude, which is one way of measuring how bright the star is. Now you do this over all the time that you are recording. So this is one point of data. Given one frame observed at some particular time, you record this flux and you do this over time and you create such light curve, what we just looked at some time back. So what are the properties that you deduce from the light curve? The very simple thing to understand is this effect of a planet going around the star is periodic, which means that it is repetitive and it depends on the orbital period of the planet. So if this happens again and again, then you can just you can model the transit light curve and look at the two dips and find out the period of the planet. Once you know the period of the planet, you can assume certain mass of the star because you know what the stellar spectral type is. So if you know that this is a solar type star, you can assume it to have a mass of one solar mass. Assume the planet to be so small that it would not make any difference. You can just assume the m star plus mp to be equivalent to m star, and then solve for this A through this Kepler's equation. Everything else is known, right? You know the m star, you know G, MP you can just assume, and then you solve for the orbital separation through knowing the P. So you can find out the orbital separation of the system as well, how far the planet is situated from the host star. What else can you do? You can also find out the transit depth. So here, this is a plot where you see the flux is drawn as a function of time. So you have fitted a light curve here and the depth from the baseline. So this is the out of transit light curve that we call. So when there is no transit happening, when the planet is not crossing the disk of the star as seen from Earth. So this is out of transit light curve. If you take the difference in the delta flux value, this actually corresponds to the radius ratio of the planet and the star. So if the planet is fairly large, this dip will be larger. If the planet is small, this dip will be smaller. and then you multiply by the total flux. So if you normalize this total flux will be 1, and the delta of F will be simply Rp square, which means the planet radius square divided by the radius of the star square, which also means that you should know the radius of the star by some means. How do you know this? Because you know what kind of star that you're looking at. You can, through models, make an assumption of the radius of the star. So the measurable quantity here will be delta F through the light curve. R star comes from the models and assumptions, and Rp is the quantity that you infer from these measurements. Now, more the number of data, you would get a good handle on this errors, like error bars on the Rp value, the radius of the planet will be smaller. If you have very noisy data like this, you see it's very hard to fit a curve. This something has been done, but the statistical significance of this data is not good. But here it looks much better. Okay. What else can you do? You can also find out if the planet is going from the center part of the disk or not. Because for the case of sun, you were able to angularly resolve the disk. You could actually see, you can actually see, the sun is the only star that you can resolve angularly. Other all stars you see as a point source. So for by default, you do not know if the planet passes through the center of the star or it passes through the limb of the star. This part is called the limb or the edge of the star. So this distance is now known as the impact parameter. So all these things can be found out once you do transit. So this is a very powerful technique to detect planets. So the first such detection happened from ground for an exoplanet in the year 2000. This was a transit light curve observed from a STARE project. So this is just name of the project, don't worry about it. And it was a ground-based data. Okay. Now, when the same target was proposed for space-based observations, you could see the quality of the data that you get out of this. It's a very nice looking curve and the error bars have gone down. The reason is because we are above the atmospheric level. All the scintillations in the atmosphere which make this data appear bad are completely gone because we go to the space. So going to space is very interesting. It makes our results very nice. It's just that it is expensive. So NASA has sent two important missions which are primarily done to search for planets around stars. One of them is the Kepler mission, which was launched in 2009. And it took a lot of data and taught us a lot about planets. And then another mission, which is currently operational, which was launched roughly a decade later in 2018. This is the TESS mission. So this produces a lot of candidates which are potentially hosting planets. And there are several other methods which go behind it to confirm if the planets exist, to find out the masses and other inclinations and other properties of the star planet system. Right. So with this, we will end the first part of the talk and move to the next part of the talk. So I think we can take questions after we finish the whole talk. So I would like to just continue the lecture. So astrometry is another technique which is to also use to detect planets. But what is astrometry? Astrometry is the science of measuring the positions of celestial objects. It will tell us about the distances to them. It will tell us about how the motions change over time. And it's one of the oldest branches of astronomy, which was used by even ancient astronomers. It's like a foundation of modern astrophysics. So now let us look at this figure. So first of all, we should understand that there is something called as the celestial sphere. Yeah, so what is celestial sphere? We are aware that there is Earth, and on Earth we have this grid. It's an imaginary grid that we place on Earth because we want to say where is different cities, where is Chennai or where is Delhi. If you want to really put those markers, you need to have a way to measure the positions on Earth. So what humans have done is that we imaginary lines we have drawn like equator or we have drawn the latitudes and the longitudes. Similarly, on the sky also, we need to make an imaginary grid to say where the position of the stars are. So it's in a way like the latitude and longitude grid. If we blow it up and let it meet the sky, then where it intersects the sphere of the sky, we call it as the right ascension and declination, or the latitude and longitude of the sky. But we do not use the term latitude and longitude in the sky. So we use the term equator for the celestial sphere We also use the same term like north celestial pole, that we have the same term in north pole of Earth, the south celestial pole, and anything which corresponds to latitude, it becomes declination on the celestial sphere, and anything which is longitude on Earth, that corresponds to right ascension on the sky. Right? So this is how you locate or you find out the position of any given star. So this is like a scale that we have drawn on the sky. Now, what astrometry actually does is it tells us about distances and the motions, and without which, of course, you cannot map what the Milky Way galaxy does, or you cannot study how the stars move in orbits. And also, if you want to understand the three-dimensional picture of the universe, this is not possible without astrometry. So it's like the 101 of astronomy, how you begin. So let us just look at this concept of what is the distance scale. Now, solar system, if you're aware, you probably know that Earth is located at a distance of 1 astronomical unit. That is the definition of 1 astronomical unit, that Sun and Earth are separated by 1 astronomical unit. In this picture, you see, this is Earth, right? Mercury, Venus, Earth, Mars. So this is roughly tens of AU, the whole solar system. That is the scale. So if you move to further objects which are further out, then this completely changes. But how do we actually measure distances? So this is the concept of trigonometric parallax. So suppose you might have observed this when you would have passed through a moving train. Maybe you would have noticed that when a train passes by, the objects which are very closer to the window of the moving train, like a pole or trees, you see that they move very fast. But any objects which are going further, which are further out, like the mountains, which you see in a distance when the train passes, you do not see them pass very fast. So this is the effect of parallax. Any object which is nearer appears to move very fast because the angle that it casts on the eye is much larger than what angle a distant object casts on us. So that is the parallax angle. So imagine this is an object and these are some distant background objects. From the point of view of this A, you want to look at this object. You notice that from this viewpoint, if the observer is here, you will associate a straight line and find that your object is somewhere located at this distant background. It overlaps with this blue square. But there is another observer, or the same observer moves to another viewpoint B. What he or she will notice is that this object is actually placed on this red colored square. So from the point of view of A, the position is coinciding with the blue square, and from the point of view of B, the position of the star is coinciding as red. So there is a change in the position only because the viewpoint, how you look at the object from what distance, the background, it changes. And if you notice, this is simple geometry. So one would be able to measure this geometry. So similar thing, it's just like the angle which is drawn here and the distance between these objects. If you know all these things, you can calculate it. So the same principle is applied to stars. So what we do is we use the position of Earth. So this is the orbit of the Earth around the sun. Okay. So Earth at this point, let's say in winter, it has some angle to look at one particular star in in contrast, like in front of the background star. So there are some stars which are too far away. They will appear like not moving with respect to this nearby star. When the Earth will complete its orbit, and after 180 days or so, like half 6 months, after 6 months, so this is a 1 year orbit. So after 6 months, Earth will be on another position, and it will reach a position, and you again look at the same star. The background star that you have behind will change. So it appears to change its position. So because of the motion of the Earth, the nearby star appears to have changed its position with respect to the background star. Now you can calculate the parallax angle because you know this distance between Sun Earth, how much this distance has changed, and then you can also find out the angle which is subtended by the nearby star. So this will be able to give you a geometry of how you will measure this. So when Earth moves around the stars, the nearby stars appear to shift. And this is what will help you measure the parallax. Now, this is measured in arc seconds. The units of this is arc seconds, and these angles are very small. So larger parallax is there when the star is closer. If the star is very, very far away from you, then this parallax is very small. So in short, the distance is 1 over parallax. So if you measure this, the angle which is subtended in this units, then the distance can be found out in parsec. So parsec is the unit of distance. That's how it is actually defined by 1 arc seconds. So let us just look at it from the perspective of trigonometry. This is the same figure, just changed it in a way where you have this the position of sun and you have the orbit of the earth. So this distance is 1 AU because we know that earth is at a distance of 1 AU, and then d is the unknown distance to the star with respect to the background stars, and then theta is something which you can measure. So based on the theta, you can always find out what this d is. Because your tan theta is 1 AU by d, you solve for this d so that you get some number in radians. You convert your theta into radians and then you find out what this distance is. So you could solve this out and you can find out. Ultimately, you lead to this particular formula where your distance to the particular star is just 1 over the theta, where theta is measured in arc seconds, and this unit will be in parsecs. This is how it is defined. So parsec is defined as the distance at which a source will subtend a parallax angle of 1 arc second. And 1 parsec corresponds to 3.26 light years. And 1 light year is the distance that light travels in 1 year. Okay. So now if you just compare how things are, so if you look at stars, they are really few parsecs away. We were talking about solar, which was just few astronomical units. But if you talk about the distance between stars, the solar system is all condensed here. All the nearby stars are still few parsecs. If you look at our size of our galaxy, this is tens of kiloparsecs. Kiloparsecs means 1,000 times of parsec. Intergalactic distances between two galaxies is of the order of megaparsecs, 10 raised to 6 parsecs, right? The distance is increased to such a big. Now our nearest, so Virgo supercluster, the part of supercluster that we are part of, like cluster is a group of galaxies. This is 30 megaparsec across. So that is a very, very big cluster, and it has several galaxy groups inside it. So that tells you how big the universe is, right? So the first satellite which was actually used to measure, so you need an instrument to measure these parallaxes. Of course, from humans, we did this experiment, or you could find out what the angle is. But these angles, as we said, is very, very tiny. So you need some nice instrument in the space to measure this. So initially, this was done by Hipparchus. This was a mission which was launched in 1989, and it looked at several stars to study astrometry. Then later, Gaia was launched in 2013, and the mission ended exactly a year from today. So 27th March 2025, Gaia saw the last time, but the data is not all out. We still have a lot of data from Gaia which will come out. But the advantage from Hipparchus to Gaia was that it will look at more stars and the accuracy will be further better. So it is micro arc seconds accuracy by which Gaia is going to look for motions. It would be able to make the detailed map of the Milky Way. So that is very precise astronomy. So the parallax accuracy is around 7 micro arc seconds for a bright star like 10th magnitude. So this means the star is much more brighter. If you go for a star which is further faint, like 15 magnitude, it is fainter than 100 times fainter than this 10th magnitude star. The accuracy goes a bit down. It's 26 micro arc seconds. If you further go fainter, then this becomes 600 micro arc second. But Gaia is able to do very good science by able to measure these tiniest of motions. Now, how do we go about looking for exoplanets with it? So the concept is that if there is a star and there is a planet which is not, so I mean, you do not look at the planet light. So you do not know the presence of the planet. You only infer it indirectly. So what will happen is the planet will, because of the force of the planet, the star will do a tiny wobble. So astrometry will try to measure this tiny shift in the position. So what we can find out is what is the mass of the planet through it, and also the orbital separation. So this will work even when the planet is non-transiting. So put this to point, I just want to show you this nice cartoon. So the positions are what we are measuring. So this is the declination, which is like the latitude on our Earth. And this is the right ascension on the sky, which is like the longitude. So this is a position of the star that is measured. You need to wait for a whole orbit of the planet. So suppose you're starting to take measurements of how this motion happens, you will start to notice that the position of the star initially is here. Then maybe after next month you again go and take another measurement of the, through astrometry, means you take another image of the, in a way, image of the star, and then you see that the position of the star has shifted in the coordinates. After some time it moves further. So once it completes the whole orbit, you see that it completes a complete round orbit or an elliptic orbit. This shows that it's a bound orbit and the star is not just drifting away, but it's completing an orbit, which means that it has a companion. Now, based on this orbit, you can always find out what, so you know the A, the orbital separation, and also the mass of this particular star, because you know what star this is, you would be able to find out the orbital period, and also you can estimate what would be the mass of the planet by solving for the orbit. With this astrometry measurements, initially there were a lot of confirmation of binary systems, which means stars which are binary. They are more than one stars, and even brown dwarfs were confirmed by this. But the issue is, if you want to search for a planet, this wobble would be very small, which means that you need to be able to measure this tiny motion, which is not very easy to do because you need very good accuracy. So Gaia, you need basically more and more measurements to do that. So Gaia over the years keep on releasing data. One data which will come at the end of this year will be able, this will enable us to detect planetary motions as well. So we are very hopeful that many more planets with this method will be detected very soon. So just to show you a cartoon, what one does is you look at such a frame where you have the host star, this is the target star, and then this is reference stars which are surrounding the target star. Now this target star is which is actually going around in different times because it has a companion across it. And then what you do is you take several frames, one frame, second, third, fourth, you make several multi-epoch images, and then through this you try to see what's the motion. The other stars will only do a little bit of tiny motion which is very predictable. You can cancel all those effects, and then you can start to see that your actual star is doing some motion which is part of an orbit, and this orbit can be solved for and find out what would be the mass of the companion object. So with this, if you try to understand how or which space we would be able to cover, then we will be actually able to look at several planets which focus on a very different mass zone, different orbital separation, because current techniques like radial velocities or transits, we have been able to detect close in planets very well, but the distant planets have not been looked at a great extent. But with Gaia, what we expect that it will start to find out planets which are further beyond their stars, host stars, very outside, like hundreds of AUs away. And this will look at a space which is not being looked at all currently, like the distance at which Jupiters and Saturns in our solar system are. And this will be very interesting to look at. So that is something which we astronomers are hoping for it. So this is the first exoplanet which was detected by Gaia. So there was some observations taken through Gaia, and it was confirmed also through radial velocity methods by monitoring through several instruments. But the first signatures were confirmed through astrometry. So this is the first planet which has a detection by Gaia, and so far other planets are not detected, but we hope there will be more with this. So I think with this, I would like to end my talk, and I would be happy to take questions.
Thank you, Priyanka, for the engaging and this nice talk. I also learned a lot about new things. So there are few questions in the chat box. I would read to them to you. If a stellar color indicates temperature, how do we account for effects like interstellar dust that can alter the observed color?
That's a very good question. So there is this concept is called stellar extinction, but the interstellar dust remains the same. So these effects get applied on top of the star. You can always predict for it because we know how the interstellar dust behaves, and this will diminish the magnitude to some extent, but this can be modeled out. So there are two things. One thing is that you find out what is the observed color and what would be the actual thing. So there will be extinction which gets applied on top of this like color magnitude things, colors or magnitudes that you determine. But since this is predictable, you know it, you can apply for it. Yeah.
Yeah. Okay. So there is another question from Smitha. Can astrometry be used to detect the presence of dark matter within our galaxy by stellar motions?
So dark matter, it's believed that it is to a large extent present there and it's uniformly distributed. So for the motion of astrometry, you have to look at certain like one how the position of any objects given change in unison or it so if you look at so basically you know how it was discovered to find out that there would be something in the center of the galaxy which could not be accounted for, how the rotation curves of the galaxies were able to detect dark matter inside the galaxy. So that was in a way very much similar to what you say, but there is nothing extra can be done because this is uniform separation. You need to understand the fact that how one is going to measure any like inter shifts between this. So this is something which is happening all together. All the stars were showing this drift based on how far they were located from the um, center of the galaxy. Yes.
So there is another question, I think, but the first question is related to that. How does multi-band photometry help in determining stellar temperature and interstellar extinction? I think the first question is also the same one. You
How
want to comment?
multi-band photometry?
Yeah, help in determining the stellar temperature and interstellar extinctions.
Okay, so multi-band photometry looks at the sensitivity of the star in a given band of wavelength. So suppose if a star is solar type and you make observations in two bands, say U or B, then the amount of magnitude that you measure or the flux that you collect in U and B will be different. Uh, for example, if you do photometry on an M-type star, because the black body peak is very different. So the amount of light that is emitted in the U band is much less than the relatively redder bands. So there will be a difference between the measurements of the two color indices, and this corresponds to some temperature. So the color and the magnitude indices are related by a very nice empirical relation. This was derived through observations. So if you measure for any unknown star, the difference between any two magnitude bands, so you choose any bands and then you try to find out the difference between the magnitudes. One would be able to estimate what's the temperature by putting it on that color magnitude diagram. I didn't get what was the other part of the question. If I have not answered everything, all you could repeat it.
It was just how does multi-band photometry help in determining stellar temperature and interstellar extinction? So I think you have answered.
Yeah, yeah.
Yeah, yeah,
Interstellar extinction also depends on different bands. So
yeah.
yeah, yeah.
There is another question. Can we detect black holes with astrometry?
Yeah, it goes to the same question,
Uh,
right? We would be
yeah,
able to detect black holes through astrometry. The answer is yes.
yeah. So now I don't see any more questions. So I would like to thank you, Priyanka, again for sharing the time and sharing her expertise. And I hope this session will be useful for the students. Now I would like to hand over the session to Praveen ji.
Thank you. Thank
Yeah.
you, Dr. Priyanka, for providing a very interesting and insightful lecture on this photometry and astrometry.
Thank
And
you.
also our thanks to Mr. Rishikesh Sharma for
Thank you.
moderating this session. Thank you once again.
Thank you.
Thank you. Thank you.
The next lecture is on plasma diagnostics from space using Langmuir probes and particle detectors by Dr. Smitha V. Thambi, Space Physics Laboratory, VSSC, ISRO, Thiruvananthapuram. We welcome Dr. Smitha to the STAR 2026. And moderator of this session is Ms. Indu Venugopal. I will briefly introduce the moderator. Ms. Indu is currently a senior research fellow at Space Physics Laboratory, working under the guidance of Dr. Smitha, the speaker of today's lecture. Her field of research is ion outflow from magnetospheres of Earth and Mars. Over to Ms. Indu.
Good afternoon. Thank you for this opportunity. So, Dr. Smitha V. Thambi is currently working as a scientist at Space Physics Laboratory, Vikram Sarabhai Space Center, Indian Space Research Organization, Trivandrum. She obtained her PhD from University of Kerala for her work from SPL VSSC in 2007 and went on to Kyoto University, Japan as Japan Society for Promotion of Science Postdoctoral Fellow. She joined Physical Research Laboratory Ahmedabad in 2011 and moved to SPL in 2014. Her primary field of research includes studies of space weather and planetary upper atmospheres and ionospheres, including terrestrial ionosphere. She has more than 50 publications in peer-reviewed journals. Currently, she is the co-principal investigator of CHASE-2 experiment on board Chandrayaan-2 mission. She has received the Booty Foundation Award, for outstanding contributions in the field of plasma science and technology in 2021, and the Nazi Scopus Young Scientist Award in the year 2017. She has also received SERB, which is Science and Engineering Research Board, DST, Government of India, Women Excellence Award in 2013. With this, I invite Dr. Smitha V. Thambi to deliver the lecture. Thank you. I'll share the screen first. I hope the screen is visible.
Yes, visible.
Thank you. Thank you, Praveenji, and good evening to all. And thank you, Indu, for the nice introduction. And I thank the organizers for this opportunity to interact with the young minds of India. So our topic today is plasma diagnostics from space. So in this lecture, we will see how the plasma could be measured in situ from space. So in situ means at the observation site where the instrument is placed, or if the instrument is in direct contact with the physical environment which we have intended to measure. So we will see how charged particle or plasma is being measured by different instruments from space. So the contents, before going to measurement and instrumentation, I'll just talk about some fundamentals of plasmas, their properties, and what is the definition of plasma. And then I'll introduce some concepts which are of temperature, energy, Debye shielding, etc. And then we will go to the space plasmas, some examples, very familiar examples in the solar system, including solar wind, terrestrial magnetosphere, ionosphere. All these are different kinds of space plasma. We will see how they are different, or what are their properties. And then how do we measure these properties, or what are the important properties and how do we measure them? A classical example of such a plasma measurement instrument is Langmuir probe. And then we will also see other instruments in brief, and we will see how the actual charged particles are being detected. So we'll take an example that is a microchannel plate, and then how this works. We will briefly see, and then I will summarize. So what we are going to study about is plasma, as you all know, which is known as the fourth state of matter, and probably a lot of matter in the universe is in the plasma state. So when we talk about plasma, we see that stellar interiors, stellar atmosphere, interstellar hydrogen, everything is in plasma state. Also, planetary ionospheres, planetary magnetospheres, and the radiation belts. For example, Earth has a vanillin radiation belt, which has highly energetic charged particles. Solar wind, coronal mass ejections, which constitute a very important aspect of space weather. All these are basically plasma. So when we go to the definition of plasma, a plasma is a quasi-neutral gas of charged and neutral particles which exhibit collective behavior. So in this case, it's a very general definition of plasma. Sometimes this plasma can be fully ionized also, as in the case of CMEs, etc. So basically, but it is quasi-neutral and it exhibits collective behavior. Quasi-neutral means the number of electrons equal to the number of ions. So basically, a particle gets charged when an electron is, or an atom gets charged when an electron is ripped away from that, resulting in an electron and a positive ion pair. And in a plasma on the whole, when we see, the number of electrons will be equal to the number of ions. And the next terminology is collective behavior. So what is collective behavior? Collective behavior means the motion of these charged particles or the plasma not only depend on the local conditions but on the state of the plasma or the field or force fields in remote regions as well. For example, if you have an electric field or a magnetic field present, the motion of the plasma as a whole will be depending on that as well. And the charged particles do not act independently within a plasma, but they respond together as a whole to the electric and magnetic fields. So that means that's called collective behavior. Now let's move on to the some concepts like temperature and density. When we talk about any generally a gas in a thermal equilibrium, it will have particles of all velocities, and the most probable distribution is generally we call as the Maxwellian distribution. A typical Maxwellian velocity distribution is shown here. And when for a plasma, for example, if we consider a gas in which particles can move only in one direction, if you take a simple one-dimensional example, and which is really true in the case of plasma. For example, if there is a very strong magnetic field and the plasma is present in such a scenario, there can be motion only in one direction, which is determined by the magnetic field. And in such a case, the width of a one-dimensional Maxwellian distribution will be characterized by the constant T, or the full width at half maximum can be defined as a temperature of that Maxwellian distribution. Now, if we talk about the mobility of the particles, as we told, these particles or the plasma particles can move in all directions with all velocities, and the most probable velocity or the average kinetic energy in this one-dimensional distribution would be E average is equal to half k to t, where k is the Boltzmann constant. So when we talk about actual three-dimensional distributions, Maxwell distribution becomes since it is isotropic, we can see that the average energy is 3 by 2 kT. So now this T is temperature and K is Boltzmann constant. Now we can see that this temperature and energy of the system is very closely connected, or the temperature in this sense means the mobility or the kinetic energy of the system. So in this case, usually we talk about temperature in terms of units of Kelvin. However, in this case, we are really dealing with very high temperatures. And since T and energy are so closely connected, we can actually represent the temperature in units of energy as well. So basically, the unit of energy, joule or electron volt, and the conversion factor is 1 electron volt is around 11,000 Kelvin. So when it, unlike a gas, something interesting happens about plasmas. As we told, the plasma is a quasi-neutral gas where ions and electrons are present, coexist. And in this scenario, the ions and electrons can have not just one Maxwellian distribution, they can have separate Maxwellian distributions with different temperatures. So plasma temperature when we define a plasma temperature, ions, positive ions and electrons can have different temperatures. So we usually denote them as Ti and Te, where Ti corresponds to the ion temperature and Te corresponds to the electron temperature. So now why these are different? Usually, as we know, a common temperature in a gas is attained by collisions among the particles. However, in the case of plasma, the collision rate among ions or among electrons is larger than the rate of ion-electron collisions. So what happens is the temperatures of ions and electrons doesn't get collisionally equalized. So temperature of electrons remain at one value, and the temperature of ions can be different. Or even when there is a presence of a strong magnetic field, the motion of the particles will be confined in one direction. In that case, even the temperatures or mobilities at two directions can also be very different, which means plasma energy or temperature is a very interesting parameter to measure and very important parameter to measure to understand the system. And we need to understand or measure the ion and electron temperatures separately. Now, plasma, when you talk about measurement of plasma, we need to understand a very important property of plasma. Plasma has the ability to shield out electric potentials that are applied to it. For instance, in this figure, if you see a positive as well as negative potential is applied in the plasma at two different points, we can see that around the positive potential, the negative charges have accumulated, and around the negative potential, all these positive charges are accumulated, which means the rest of the plasma, the electric potential which is being applied, is shielded out. So this shielding is known as Debye shielding, and the average shielding distance is known as the Debye length. The Debye length is defined as in this relationship, where we can see that apart from the constants, there is temperature or the energy of the plasma and the number density. The E is electric charge and the number density of the plasma also. So when the temperature is more, the Debye length becomes more. Similarly, when the plasma becomes very tenuous or the number density is very less, the Debye length becomes more. So basically, if you reduce these constants, this becomes this kind of a relationship where T is the directly proportional and N is inversely proportional. And for this relationship, we have put temperature in Kelvin. So, which means that if there is a when we talk about a plasma system, if the dimension is larger than lambda d or the Debye length, then whatever local concentration of charges arise or electric potentials introduced, these are shielded out in a distance of about L, leaving the bulk of the plasma free of electric potentials or fields. So in this case, the rest of the plasma is free of any potentials or fields. So that is called the Debye shielding. So when we try to measure a plasma, this property becomes very, very important. Now, with this very fundamental understanding or very basic understanding of plasma, we understand that plasma is made up of charged particles, and there can be temperatures of or energies can be in the terms of very high temperatures, and it can be represented in EVs. And then we also know that ion and electron temperatures can be different in many scenarios. And also we understand that magnetic field and electric fields can influence the plasma in a collective manner. Also, we understand that they can shield this in a small distance called Debye length. Now, when we go to real life examples, we will go to the solar system plasmas. One is the solar wind. Solar wind basically is a continuous stream of charged particles, mainly electrons, protons, and alpha particles, that is He double plus, emitted from the sun's corona into the interplanetary medium. And this, along with a magnetic field, it travels every part of our solar system. So basically, the sun has a magnetic field, and since it is a gaseous ball, it has a very interesting structured magnetic field. And it also, when these particles come out, it also comes with the magnetic field associated with it. So the stretched solar magnetic field basically end up in a spiral shape because sun rotates, and it rotates differently. Like equatorial and polar regions have slightly different rotation, which we call as differential rotation. And the magnetic fields, when it stretches out, it forms basically a spiral, which we usually call as Parker spiral. So the Parker spiral provides an umbrella-like structure wherein you have hot plasma or the solar wind, which touches every part of our solar system. It comes to all the planets and planetary bodies of our solar system, with, of course, changes in densities and magnetic field with respect to distance. So typically at Earth's distance, the density of these particles is around 3 to 10 particles per centimeter cube. Velocity of the solar wind is around 400 kilometers for a slow solar wind, and Sun also produces fast wind from regions, say coronal hole regions, wherein this can go up to 800 kilometers per second. The proton energy can be around 1 to 3 keV, kilo electron volts, and which has a magnetic field of around 2 to 10 nanotesla. These are all during quiet times, whereas during active space weather events, these values can enhance. Now going to the second example, that is, so the solar wind, basically we can call it as a fully magnetized hot plasma, which is in terms of temperatures or energies, they are highly energetic. And this, since they are closely associated with the solar magnetic field, we call it as magnetized plasma. So this is a fully magnetized hot plasma. Now when we talk about another, we'll go to another example, that is terrestrial magnetosphere. Not only Earth, planets like Jupiter also has an intrinsic magnetic field. So a magnetosphere is a region around a planet which is dominated by the planet's magnetic field. As you all know, Earth has an intrinsic magnetic field which protects our planet from the incoming charged particles or the solar. Basically, it deflects the solar wind. So it's basically a very vast magnetic bubble, as you can see in this picture. It's very dynamic, and this can deflect the charged particles as it encounters or it comes from the sun. So solar wind gets deflected, and there will be this solar wind comes, as we saw, in a very high speed, supersonic speed, and the solar wind becomes subsonic in this region, wherein a shock is created that we call as a bow shock. And then between the shock and the magnetopause region, that is where the magnetic field weakens and ends. The magnetopause is there, and the usual dipolar structure is compressed in the one side by the solar wind, so that's a day side, and in the night side it is elongated, where we call it as a magnetotail. And there are different regions like lobes and tail region, plasma sheet, etc. The number of particles differ in each region, and as in the case of energy also. So like for example, the plasma sheet may have 10 eV to 50 kV kV particles, whereas the radiation belt may have particles more than 400 keV also, and even relativistic electrons wherein energies can be more than 1 MeV. So this actually hosts a very interesting plasma system where you have different kind of particles with different energies and different kind of densities also. So this is another example of a very dynamic plasma system which we encounter in the space. Now, coming down a little bit, we have another interesting plasma, which is the terrestrial ionosphere. So a typical temperature structure is of the Earth's atmosphere is seen here. Very familiar terms: troposphere, stratosphere, mesosphere, and thermosphere. And the ionosphere, as we can see, is a part of the thermosphere. When we talk about thermosphere, we generally talk about neutral particles, and ionosphere is the ionized component of the thermosphere. Or we can see here the plasma density in the x-axis and altitude in the y-axis. You can see that the ionosphere starts below 100 kilometers, and it can go around above 1000 kilometers also, wherein it merges with the plasmasphere and then the magnetosphere. So here you can see that the maximum number of particles is around around 300 kilometers in the F region, and that we call as the F region, and below that what we call is E region and D region. And you can see there is a day-night variation in the plasma density. But here the composition is O plus is dominant and the densities are much higher. We are talking about particles like 10 raised to 6 particles per cc also. And in this case, we have so much of neutrals present, almost several orders more than the ionized component. We have neutrals also present. So we will have to talk about three temperatures, that is neutral temperature, ion temperature, and electron temperature. So electron temperature being the highest is also less than 1 eV or typically less than around 5,000 Kelvin. Wherein in the previous examples, what we saw was much higher, like keV, MeV particles. And then these are the ion temperatures typically. So this is a partially ionized, and we can see that since the temperatures are low, we can tell this is a cold plasma. This is ionosphere. And just to show you another aspect, the ionosphere or the is also like magnetosphere. We saw that there are several regions and structures present. Ionosphere also has structures, and this gives you an example of how a magnetic field. These are field lines, terrestrial magnetic field lines, and how the field lines control the plasma motion and get plasma structures in the ionosphere. So this is how Earth's ionospheric plasma becomes highly structured due to the presence of large-scale structures get generated due to the presence of the magnetic field, and these are typical values of electron temperature. So whenever electron density gets structured, electron temperature also will have lots of variability. So, and as we know, the electron temperature, electron density, all these parameters can vary with altitude, as we saw here. Local time, as we saw in the previous plot, day and night has variations, and season, solar cycle, space weather, everything is affecting the variability of ionosphere because it's primarily produced by the solar UV radiation, and the variability associated with that will affect the ionosphere to a great extent. Now, what all we want to know about plasma? So we want to measure our electron density, which is equal to the ion density because plasma is quasi-neutral. It's Ne equal to Ni, and electron temperature. But when we talk about temperature, electron temperature and ion temperature becomes not equal. We need to measure them separately, and then we need to understand the composition of ions in terms of what are the dominant ions, whether it is O plus, whether it is CO2 plus, etc. when we go to any planetary atmosphere. And then when we go to very low densities, we talk about the density, not just in terms of number density, we talk in terms of flux and energy when we go to the energetic particles, slightly more energetic particles and more tenuous plasma, because flux means we are multiplying that with the velocity or the motion of the particles, and then energy also should be known. Now, let us take the very familiar example of the ionosphere, that is the region which is nearest to us, and where we want to measure the two. Let's try to measure two parameters. One is electron density and temperature. That is done by a Langmuir probe. So what's it basically a Langmuir probe? A Langmuir probe is nothing but an electrode which is inserted into the plasma, and then we apply a potential, varying potential, electric potential, and then the current collected by this electrode is measured as a function of the applied potential. So what we basically get is a voltage current characteristic, wherein current is measured as a function of the applied voltage, and from this IV characteristic curve we can get the electron temperature and electron density. So here is a typical example of the electrode. So electrode can be a sphere. Here we are seeing the example is a sphere, and that it can be a plane, or it can be a cylinder, or even a thin wire. Cylinder in the sense it can be a thin wire also. So any of these shape electrodes can be inserted into the plasma to measure these properties. So now what we get is basically the current voltage characteristic. Let's see how it looks like. This basically is the current voltage characteristic curve, very idealized curve, where x-axis gives the probe potential or the applied voltage, y-axis is the probe current, which is given depending on the plasma parameters. So in this curve, we have three regions. One is the ion saturation region, the second one is the electron retarding region, and the third is the electron saturation region. So let's see one by one of all these regions. So now we started with a negative potential, and when the potential is negative, obviously the electrons are repelled and the ions reach the probe. Now the positive ions are reaching the probe and the ion current is getting collected. So the collected current is nearly constant here, and you can see that the current is negative in usual convention. Now the current is now dominated by ions here, and actually speaking, technically, this is a measure of how many ions are present or how much ion density is present. So you need not, if you think ideally, this should give what is the ion density, but that is really difficult, and that's why we try to measure the electron saturation and electron density. Why this is big? Why this is difficult? Because ions are less mobile compared to electrons, and ion current is then small and strongly depending on conditions. For example, sheath conditions. Sheath, I'll come a little later. And then this is actually not, in practical cases, we see that this is not as clear as distinct as in the case of this idealized curve, and this is very sensitive to noise and offset. So we don't really measure the ion densities or using a Langmuir probe. We just keep on applying the potential, and now the probe potential becomes less negative, and now we can see that some electrons which have enough energy to overcome this potential barrier reach the probe. So electron current starts appearing, and when then we go on changing the probe potential, and we can see that at one point the electron current, the probe potential becomes positive, and then it starts attracting electrons, obviously. Now at one point we can see that the electron current or the number of electrons getting attracted to the probe becomes very high, or the electron current increases exponentially with the probe voltage. So this is a region which is very important for, this is called the electron retardation or transition region, which is very important for determining the electron temperature. This, simply speaking, how an electron comes to a probe when a positive current is applied, it varies with the electron energy. So in a small potential, the electrons which are having enough energy will come. When the potential increases, more electrons get attracted. So it's a measure of the energy or mobility of the electrons present in the plasma, which means that by analyzing the electron retardation region, we can get the electron temperature or the energy of the electrons, incoming electrons of the plasma. So that relationship is like this. The electron current here is proportional to the the voltage, and inversely proportional here, the exponent inside the electron temperature. So from this equation, we can derive the electron temperature. Now, when we go to further positive, we reach the electron saturation region. Saturation means almost all electrons have reached the probe and the probe current is collected. Now, no more electrons will come. So electron current becomes a constant, or electron current becomes larger and it gets saturated, which means the current is dominated by electrons and no more electrons are there. Almost all electrons in the medium has reached the probe. So this can be used to determine the electron density, but the expression is here, which also has the electron temperature. So the electron retardation region, when we have measured the electron temperature, and that temperature goes into this expression, and electron density can be estimated. And there are other ways also to determine electron density, which will come in a moment later. So when I was speaking, I was talking about plasma potential. The plasma potential is where the electrons getting electron collection becomes very strong, or it's kind of a near region where your strong electron collection begins. That is called the plasma potential. And before that, there was a point from where this ion current was changing over to electron current. There was a point where the probe current was zero. That region is called as the floating potential, where the plasma or the probe really floats in the plasma. So this floating potential is very important. We will see in a moment later. Now, simply placing a Langmuir probe to a plasma we will not be able to measure the plasma parameter or electron temperature or density accurately. So that's why the Debye criterion length becomes very crucial. So what happens is like this: when there is a satellite present and the satellite wall, initially you assume that the satellite wall was uncharged. Now, what happens is it is residing in a plasma. Now, we see that plasma has both electrons and positive ions, but electrons are more mobile than the positive ions. So, initially, when the wall is uncharged, lot of electrons will hit the wall of the spacecraft, say. And what happens is once the wall gets hit by a lot of electrons, a negative surface charge will develop. It will prevent further electrons to hit the wall. And now here the ions will be more attracted because it's already negative. So in this region, this Ni becomes not equal to any. That region is called the sheath region. And after the Debye length almost, we will see between this slowly that condition will become Ne becomes Ni. But here also that is called the pre-sheath region. But still in this region the plasma will be perturbed because we are still in the Debye sphere, and then above the Debye length we will get undisturbed plasma. So anything, the probe should be facing the away from the satellite wall at a distance much more than the Debye length of the system. So that means we should know what is the typical electron density and electron temperature when we design a Langmuir probe. And if it is a typical ionospheric plasma, the Debye length is few centimeters. So the probe should be placed at a few centimeters, I'll say 30 centimeter away from the satellite wall, and that is precisely why this boom is seen here. Not only that, the radius or the size of the probe also should be small enough, otherwise the sheath generated will be very big. So the size of the probe should also be very small compared to the Debye length to have very efficient or accurate measurement of the plasma. So this is how a Langmuir probe is designed, and it measures the electron density and temperature. So this is an actual example of a Langmuir probe, which is called the Ramba LP Langmuir probe on Chandrayaan-3 lander, which was designed, which is by ISRO. SPL has developed this instrument, and this has measured the tenuous lunar plasma. So you can see that since the plasma is very tenuous, the densities are very small, the length of the boom is also much higher, and this kind of an instrument was deployed from the lander. Now, there are other variations also of the Langmuir probe, where for one example is the electron temperature probe, wherein very accurate TE measurements can be obtained, not just by sweeping, but slightly a different method. Here, the sensor is divided into two hemispheres, and one hemisphere is called the reference electrode, and the other one is a signal electrode. So as we saw, there is a potential called a floating potential, where the probe current becomes zero, and the floating potential changes if we apply a sinusoidal voltage to the probe. So once we use a reference and in the other side we use a sinusoidal, the difference in the floating potential is measured, and which is actually a measure of the temperature. So this gives a more direct measurement of the temperature, wherein a voltage sweep is not required, whereas what we want is only a sinusoidal voltage in one of the hemispheres. So this was designed by the Japanese in 1970s, and which are being used in several rocket and satellite experiments. Now this can also give density by a different principle, wherein the frequency is swept. When we are giving a sinusoidal here, we are giving a constant voltage, constant frequency. But here, what we are giving is the frequency is varied. Then we have different plasma resonances happening, from where we can measure the electron density. So these kind of variations in Langmuir probes are also available. And now, since we talked about electron temperature and electron density, and we saw that the ion density is still difficult to measure using a Langmuir probe, we have another instrument called the retarding potential analyzer, which can give the ion temperature, drift velocity, and ion density. Here, what we do is retarding voltage is applied to the grids, and certain energies only will pass through, whereas the lesser energy or according to the voltage, some of these particles will be rejected and some of these particles only can pass through. So the retarding voltage, if you are sweeping, there will be a collector and the collector current will vary. So depending on the energy of the particle. So basically what we get is the energy distribution of the positive ions here, and then we from there we estimate the ion temperature, velocity, density, etc. Now, when we, as I told, when we talk about very tenuous plasma, like the solar wind, we talk about particle flux and energy, or even in magnetosphere, we talk about particle flux and energy. A Langmuir probe cannot be used to measure such plasma because it becomes so tenuous, the sheath becomes so large, your dBi length becomes in terms of very, very large in terms of meters and meters. So that can, and the current becomes, when the, since the plasma or particle density is so low, the current becomes so small, which cannot be measured. So dBi length also becomes very large, and so the practical Langmuir probe measurements are not possible for such plasma. So therein what we do is we actually detect each particle by particle. That is done using electrostatic analyzers. So electrostatic analyzers are basically instruments which are used to measure the energy and angular distribution or the directionality of particles by, as I told, plasma particles will have directionality, especially when the presence of a magnetic field will make it so directional. So we can use electric fields to selectively allow particles to us with a specific charge, energy per charge range to reach detector. You can see here there is a curved path for the plasma particles, and different voltages are applied here. You can see that these particles with these energies hit the wall of the surface, and particles with only certain energy passes and reaches the detector. That's the correct energy bin for this particular voltage. So when we change the voltage, a particle with a different energy can also reach the detector. Like that, we can differentiate the particle in terms of their energy, or more precisely in terms of their E by Q. Now, not only that, we want other information like particle mass also. For that, what we use is time of flight analyzer. So time of flight analyzer is like this. When a charged particle enters the instrument, we somehow try to understand that it started at one point and then it stopped at another point. For example, if a carbon foil, very thin carbon foil is present, placed near the entrance, and the particle enters the particle, and we are sure that the particle has crossed the carbon foil, then we see that the time at which the particle hits the carbon foil gives the start pulse. Now, at some distance away, there is another foil, which is a thick carbon foil. Now it hits the carbon foil and it doesn't pass further. So which means that the particle is stopped there. So between the start and the stop, if the particle's path length is known, then you know the velocity of the particle. That is how much time it took for this particle to travel that much distance. So that gives you basically the velocity. And then if we know the energy per charge, then we can actually determine the particle mass. So when we have a combination of electrostatic analyzer and the time of flight segment, we can get energy and then the particle mass also. So basically, entrance aperture wherein the particle enters, and then there is an electrostatic analyzer where the particles are analyzed with voltages to understand their energy per charge, or it selectively reaches the detector at one point with a different energy per charge, and then we want to start the all the particles should receive an equal amount of energy. So for that there is a post acceleration, and then when these particles start with an equal amount of energy and then allowed to transit a certain distance, their speeds will be depending on their mass. So there will be a start signal and a stop signal, and the time of flight section where the particle travels a known distance. From there, the velocity also is estimated, and from there we get the mass because energy is already known. So this is such a system which is from the MAVEN static instrument, which is for the Mars mission by NASA. So you can see that in the entrance apertures, there are some deflectors which will be telling about the direction. And then for the energy and charge, there is an electrostatic analyzer section and followed by a time of flight section where the after that the post acceleration is by minus 15 kilovolt, and then this detectors are MCP. So basically, you don't have to go into the details where we have the, as I told, there is a thick foil and there is a start foil. So from the start foil to the thick foil, the gap is 2 centimeters, and the time of flight in this 2 centimeter region between the stop and start carbon foil is used to measure the mass of the particle, wherein the time signals are converted into digital, and the other controllers and high voltages for this instrument work are given here. So we have also built a similar instrument for our Aditya L1 mission, that is called the PAPA instrument or the plasma analyzer package for Aditya. This can measure the solar wind in the range of this 0.01 to 3 kilo electron volt for electrons and 0.01 to 25 kilo electron volt for ions from the L1 point of the Sun system, and this has different sensors for electron and ion. You can see that there is a electrostatic analyzer section and there is a time of flight section and all that. And UV trap is because we do not want secondary electrons generated by the UV falling on the instrument. So that we will know once we talk about the detection. So the detectors basically, as I told here, one of these detectors very widely used is MCP. So how the MCP works is as follows. The microchannel plates are very sensitive for electrons, ions, or even photons. That's why we really want the UV trap when we are trying to measure the electrons and ions. So basically, these are glass channels, 10 to 100 millimeter in dia. And what happens is that this is basically transparent of around 60 centimeters. So you have very, very tiny holes here, as we are seeing. This dia of these holes is around micrometers. And then this glass lead glass channels are actually coated with something which can produce secondary electrons very easily. Example, a very popular choice is silicon dioxide. So this silicon dioxide layer will be inside these channels, and when a particle hits here, it generates a lot of secondary electrons. And if you stack here these MCP plates like this, then you can get, for one particle, you can get something like a 10 raised to 3 to 10 raised to 7 electrons, and which is very easy to measure, or we can actually detect those particles. So this is how actual charged particle is detected by the instrument. So such detectors are placed here, and the other region we have a lot of voltages to control or the trajectories of this, and then measure the time of flight, etc. So this is how basically a plasma particle is measured in situ in space. This is the case of energetic particle. When the energies are low and the plasma is dense, the debye length is small. In terms of centimeters, there we can use instruments like Langmuir probe, wherein the probe is basically a conducting electrode, and the current collected by the conducting electrode is with respect to the applied voltage, which is varying, can give the basic properties of the plasma. So in summary, what we have seen is that we measure the space plasmas in situ which provides us direct local sampling of density or flux, temperature or energy, potentials and fields also. And what we have not talked about in this lecture is electric and magnetic field measurements, which are also important to understand the physics of space plasmas. So in this context of exploration of solar system bodies, planetary science, these experiments are used to study ionospheres, magnetospheres, space weather, solar wind, and in its interaction with planetary space environment. Yeah, thank you. So I think we have. Oh, yeah, we have few questions. One is about how does the interaction between solar wind and planetary magnetic field affect the space environment of planets? Yeah, this is very correct. As we saw, if a planet has an intrinsic magnetic field, it can deflect the solar wind which is coming from the sun, and then it protects to a great extent. But now, for example, when a space weather event comes, or when the interplanetary, and as I told, the solar wind comes with the magnetic field also, and if the magnetic field direction of the magnetic field is in or direction opposite to that of the earth's um, earth's magnetic field, then there is a process called reconnection happens, and the particles from outside can enter. So these energetic particles, solar wind particles, when enters the earth's space environment, it can actually create energization, ion outflow, etc. And you can see auroras, for example, during space weather is a direct evidence for the interaction of the solar wind or space weather events with respect to the planetary ionospheres. And in the case of a planet which has no intrinsic magnetic field, we can see that there is only an induced magnetic field, because the charged particle or the ionosphere is charged particle in motion, which can create an induced magnetosphere. Otherwise, the solar wind can directly come and strip away a large part of the ionosphere, the charged particles. That is why we see that the Martian ionosphere or magnetosphere, when we see one process called ion escape, which is very dominant due to the solar wind interaction. Okay. These men, as I told, there is another question. What kind of instruments are used in different regions? For example, when we talk about thermal plasma or very cold plasma on the, for example, in the case of ionosphere, we call it also as the thermal plasma. And these can be, as we saw, these can be measured by the instruments like Langmuir probe and retarding potential analyzers. Whereas when we talk about magnetosphere or solar wind, when we are talking about KeV or MEV particles, we have to have this electrostatic analyzers, time of flight detectors, and etc. To get the particle flux in terms of the particle flux. In terms of detectors, we have different kind of detectors. For example, what I told in this lecture is microchannel plate, one kind of a detector. Another is channel electron multipliers can also be used. And then we also have people have been using solid state detectors to measure the composition or the energy. So basically, the composition is measured using the time of section, and mostly we can use the microchannel plate as a detector here. This is a very important question. How the Langmuir probe account for the photoelectron effect when exposed to direct sunlight? This is a process which is very important, because the photoelectrons can be generated, and this can also be detected. So this is very much there. This is one of the error sources in the Langmuir probe detection. We can take care of this in terms of calibration. Also, we will be using some coatings which can reduce the photoelectron effect. the density, why the most of the visible universe is composed of plasma? Because they are, most of these particles like interstellar hydrogen, etc., are in the charged state, and even if there is a low density, they exist. Plasma can be very tenuous also, even when and being tenuous makes it more probable to remain in charged state because there are no collisions or less collisions. So when the atmosphere becomes very, very tenuous, your existence of plasma becomes more viable. How does the spacecraft potential affect the Langmuir probe measurements? It affects very much. And that is why we always use long booms. In the case of Langmuir probes, we use booms of several centimeters because this should be away from the spacecraft potential, and the applied potential always will have. And that's why I told the idealized, what I showed you is a very idealized Langmuir curve. In the case of actual scenario, this will never look like this, especially in the case of very high spacecraft potential regions and all. So we will be able to correct these effects using very careful calibrations and so on. So that's why the Langmuir probe technique, though it looks very simple, it's not. It's not as simple as it appears. It has a lot of complications in terms of spacecraft potential, photoelectron effect, etc. So the material of the boom, the material of the probe, all these things are determined. Length of the boom, all matters very well. The applied, what is the voltage range we apply, all this matters for a very meaningful measurement of the plasma. And that's why some of these electron temperature probe which I showed you, because that gives a reference and a signal electrode, and the difference is taken. So most of these effects gets nullified because you already have the measurement in two spheres or two halves. So that's why many times we use such advanced versions of Langmuir probes also. Yeah. I think those are the questions, and let me hand it over to Praveenji. Thank you.
Thank you, Dr. Smitha, for a wonderful lecture, very informative, and you have covered a lot of fundamentals related to plasma physics and other things, including instrumentation part. Very good lecture on this, plasma diagnostics. And also our thanks to Ms. Indu for moderating this session. Thank you, both of you, to be part of this program.
Thank you, and my best wishes to all the students. Have a great time and do well. Thank you. Thank you, Praveenji.
Thank you.